right, so we're going to do one more example of looking at a limit involving this indeterminate form of 0 over 0. So what we saw in our last couple of examples is that we need to do some sort of algebraic manipulation. Eventually we'll get into trig identities as well for trig functions, but if it's potentially it's factoring and reducing if you have a rational function, a polynomial over a polynomial. If you have something involving radicals, a lot of times that'll be your prompt to multiply by the conjugate. An important thing to realize in these situations is that as you go from step to step, you want to still keep your limit notation because the limits of these functions are equal. The actual functions themselves, when you reduce a factor over a factor, what's causing that 0 over the 0, when you reduce that, you are changing the function. Albeit you're just changing it at one point, but you are changing it. So the functions themselves are not 100% equal, but the limits of the functions are equal. And so what's really happening, you kind of see it in the thought bubble there on number 4, is there really was a little hole in the graph at x equals 3. And when we reduce that x minus 3 over x minus 3, we change the function by filling in the hole. It does change the function. It defines a point that wasn't there before, but it allowed us to find the limit. And so that's what we're doing with these problems. All right, so I just wanted us to take a look at one last example. Limit as h goes to 0, f of x plus h minus f of x all over h. So as you look at this one, it's going to feel more abstract a bit, and it's going to feel somewhat maybe kind of just like arbitrary, like, okay, I have to put in this function and it's this limit as h goes to 0. But it's an important limit to start to work with because this limit, and there's going to be another one that you're going to see probably in your homework that's going to look like the limit as x approaches a number of f of x minus f of a over x minus a. These two that are going to feel just a little bit more abstract are actually going to be limits that we come back to when we define our big topic we're kind of building towards here is going to be the definition of the derivative. If you remember from the opening video, the slope of the tangent line. So it's an important example is all I'm saying here. And you'll see it again. You will see it again. So on this one, though, it's the limit as h goes to 0, but I have this f of x plus h and f of x, and so I actually need to start by kind of writing out what that means for this particular example when we have f of x equaling this negative 3 over x. So it looks like the limit as h goes to 0. So f of x plus h says we go into the f function. Every place where there was an x, we are replacing it with the x plus h. So we have negative 3 over x plus h. And then we have minus the negative, f of x is negative 3 over x. So we end up with minus the negative 3 over x. And this whole thing is over h. All right, well, certainly, you probably see that minus and then this negative and change that to addition. That's good. But suppose you started off in a similar line of thinking and you just said to yourself, I'm going to just try direct substitution, right? I'm going to put in 0 for h and see what happens. So if we did that, we'd have negative 3 over x plus 0. So 0 in for h, x plus 0 would just be x. And then we'd have plus 3 over x, because remember, h is going to 0 here, not x. But then in the denominator, h is going to 0. So, of course, negative 3 over x and plus 3 over x are going to be 0. And we have 0 divided by 0. So we do have another example here of what we call that indeterminate form. So answer is literally not determined yet. So this doesn't look like the last two in the sense of, I don't see factoring to do, I don't see radicals that make me think multiply by the conjugate. So really the only thing we can do here is just work on our, we're always just trying to do some sort of algebraic manipulation here. So what can I do with what we call a complex fraction? So remember, complex fractions are fractions within fractions. And there's a couple of different ways. Typically the first way, if we're doing this in class, if I kind of throw this out to students, usually the first response I get is, well, get a common denominator. And that's a fine way to go. So that's what I'm going to start with. So let's say I do just that. And I get a common denominator, which really means I'm focusing on this adding of these two fractions in this numerator. So the first denominator is x plus h, and that is different than the factor of x, which is in the second denominator. So each of these fractions have to be multiplied as a version of 1 by the other denominator in order to get a common denominator. And then the whole idea is now we can put the operation of these numerators over our common denominator. So what would we then have? Well, we would have our limit as h goes to 0 of negative 3x, and then we have plus 3 times x would be 3x, and then the 3 times the h, so I'm distributing through that 3, would be 3h. And that is all over my common denominator, which is x quantity, x plus h, and that whole thing is divided by h. All right, now certainly the minus 3x and the plus 3x are going to become 0, so those are effectively gone. And then what I want us to think about is we still have a complex fraction here, but the beauty of getting this simplified down to one fraction divided by one fraction is that now we can bring this up as multiplying by the reciprocal, and what we'll now have will look like our limits as h goes to 0, and we have the 3h over the x quantity, x plus h, and now times the 1 over h. And we are finally to a point where we can reduce the h over h. And just like the last two, when you get to that point where you do that reducing, that's going to typically be your prompt that you're going to try to reevaluate after that. So there's the 0 over 0 issue, right? H over h, you just saw it kind of get reduced there. So now let's just go ahead and evaluate this limit. So we now will drop our limit notation and say 3 over x times the quantity of x plus, and for h is going to be 0. And so what makes this one a little different, of course, it was a little more abstract, and our final result is actually not just a constant here, it's a function, a 3 over x squared. So again, where we're headed with this is you may kind of even recognize this f of x plus h minus f of x all over h. If you had that maybe in college algebra or pre-calc, that's the difference quotient. And so we're really kind of building up to that's going to be one of our definitions of the derivative that we actually just worked with there. But here, it's just another limit exercise for the time being. So that's our last example in 1.2. When we come back next time, we're going to start talking about something that I've been mentioning to you as you're evaluating limits, and I'll say things like, oh, well, if it's continuous, then you're able to use direct substitution, like polynomials, for example. But we haven't really given a real strong, concise definition yet of what continuity is. And that's what we're going to talk about in 1.3. We're going to get a real precise definition of continuity, and we're going to talk about some different types of continuity. So we will come back to that next time.